This video is the middle of 3 videos that introduce the topics of intermolecular attractive forces. If you have not watched the Introduction to Intermolecular Attractive Forces video, you need to stop and go take care of that first. You also want to be familiar with how to do a Lewis dot structure and how to determine the polarity of a molecule. Intermolecular attractive forces. We have 3 types: hydrogen bonding, dipole-dipole, and London. Hydrogen bonding is the strongest of the 3. Dipole-dipole is the middle, and London is the weakest. Now, the context of who's the strongest and who's the weakest in this is that we're talking about small molecules, so molecules that have only one central atom. When we talk about really, really enormous molecules, it turns out that only London forces come into play, and so then we just look at the mass of the molecule. But when we're talking about small molecules, so something like X and it's got Y, 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 Y attached to it, it's a small molecule, and so we can distinguish between hydrogen bonding as a strong force, dipole-dipole as sort of the middle, and London as the weakest intermolecular attractive force. Since these intermolecular attractive forces have different strengths, they can have an impact on the physical properties of liquids. The stronger the intermolecular attractive force is, the more energy is required to separate those molecules from their neighbors. So if you think about, for instance, a couple of molecules that are in the liquid phase, kind of close together maybe, we think about them as having some intermolecular attractive forces between them, not a bond, but an intermolecular attractive force. When we go to the gas phase of this liquid, we have to separate these molecules from each other and spread them out. That's what happens when you move from a liquid to a gas. So that means you have to overcome those forces that were between the particles. So the stronger those forces are, the more energy you have to put in, and the higher your boiling point or your melting point would be. So that also brings into play what is boiling point and what is vapor pressure, because those are 2 physical properties that are impacted. Let's talk about vapor pressure first. It's the pressure exerted by the vapor above a liquid when the liquid and vapor phases are in physical equilibrium with each other. Physical equilibrium is the state in which you have 2 things happening and they're opposite of each other and they take place at the same time. So it's kind of like people entering and exiting a building at maybe like a government building where you've got a lot of people coming in and a lot of people leaving at the same time. A vapor is that gas that's above a liquid that you only have there because the liquid actually lets molecules go into the gas phase, not because you boiled it or did something to it. So over here I've got this happy little picture of some particles, and these guys are jumping back into the liquid phase while these guys are jumping from the liquid phase into the gas phase. And what happens is all of these guys here in the gas phase, they can bounce off the sides of the container, and when they do that, it creates pressure. So we get pressure from collisions between the molecules in the sides of the container, and the more molecules I have in that gas phase, the higher the pressure is. So when we think about vapor pressure, in order for molecules to leave the liquid phase and go to the gas phase, they have to overcome the attraction they have to their neighbor. So if they have really weak attractions, then I'm going to have lots of particles in the gas phase, and I'll have a high vapor pressure. If instead, so weak intermolecular attractive forces will give me high vapor pressures. I think my next slide might actually say this as well. And really strong intermolecular attractive forces, so they really like their neighbors, not so inclined to jump from the liquid phase to the gas phase, those give me really low vapor pressures. Boiling point comes from the fact that there is some temperature at which the vapor pressure of the liquid equals the atmospheric pressure, so the pressure that's felt by the liquid. Normal boiling point is the boiling point that occurs at 1 atm of pressure. When we look at what a pressure cooker does and how it cooks food faster, a pressure cooker essentially is a container that has really applied a lot of pressure. So we've got high pressure in here, on the food, and and so your food cooks faster because you boil at a much higher temperature. High altitude cooking, on the other hand, when you go to the top of a mountain and you're cooking, you'll find that your water boils at a much lower temperature because atmospheric pressure is lower, and so your food takes longer to cook because there's not as much energy being transferred because the boiling point isn't as high. So let's consider carbon disulfide, water, and PCl3. And in order to answer the question of who has the highest melting point or the lowest boiling point or the highest vapor pressure, we have to consider who has the strongest intermolecular attractive forces. That's really what this question is asking. So we want to know the strength of the intermolecular attractive forces. And to do that, we have to identify what the intermolecular attractive forces are by drawing a Lewis-Dot structure for each of these. For water, you probably don't need to really draw the Lewis-Dot structure at this point, but we'll just be thorough and take care of that. And what we notice is that CS2 is a nonpolar molecule, and so therefore its strongest intermolecular attractive force is London, which is pretty weak. Water, on the other hand, has that OH bond, so we know it has hydrogen bonding as its intermolecular attractive force. That's pretty strong. PCl3 is a polar molecule that doesn't have OH, FH, or NH bonds, so it has dipole-dipole as its force, and that's in the middle. So now we know that the highest melting point will come from the substance with the strongest intermolecular attractive forces. Because highest melting point means I have to put a lot of heat into the system in order to overcome the attractions between the particles to get it to move from a solid to a liquid. So the highest melting point will be water. The lowest boiling point, on the other hand, is going to be the one with the weakest intermolecular attractive forces because I didn't have to put as much energy in to get it to boil, and so that will be CS2. The highest vapor pressure will come from the molecule with the weakest intermolecular attractive forces because we're talking about lots of pressure coming from this vapor, and so this will be CS2 as well.